Hey, this is Leach with Simpson Math, and in this video, we will be wrapping up our discussion of conics with the hyperbola. Now, here's my preface for the hyperbola. If you recall from the last video with the ellipse, that if we add up the sum of the distances from the foci to the point on the ellipse, that it's always the same, which was 2a. But now we're dealing with the hyperbola. And so instead of the sum, we're going to be looking at the difference. So if I subtract this distance and that distance, then we always will get the same value. So every point on the hyperbola will have the same value, which actually turns out to be 2a. So let's look at why this is. So in this particular hyperbola, the distance is always 6. But let's say I'm wanting to find that value right there. So if I have my distance from this focus, it's my c, which my c is my focal length from the center to the focus, plus the a, which the a is the horizontal distance from the center to the vertex of the hyperbola. So if I add these up, I get c plus a. So this distance right here is ca. And then the distance from this focus to that same point is, well, this distance right here is c, this distance right here is a, so if I do c minus a, I get this. So if I if I subtract, if I do c plus a minus c minus a, notice when I distribute, these c's will cancel to 0, and we're left with a plus a, which is then our 2a. So every point on this hyperbola, if I take the difference from the difference of the distances from the focus to the point, they will always be the same. All right, now this time let's talk about the relationship between our A, B's, and C's. So this time we need to look for that right triangle relationship like we did with the ellipse, but on the hyperbola, the hypotenuse is C. The reason why this is different is because our foci are outside of the distance of our A's. If this was an ellipse, our foci would be inside, but here this time our foci are outside of it. So my longer value between my A, B's, and C's are always going to be my C's. So that's our hypotenuse. There's other mathematical reasons for it, just like I could have done. I could show you with what we talked about in the ellipse video, but just at this point, just trust me, it's this relationship. So we can find C by basically just doing Pythag. Square root of a squared plus b squared will end up giving you our C. A few other little just tidbit differences. So we have these two axes again, but this time we call this the transverse axis. It's the line, the axis that goes through our foci, our vertices, and our center. And then the axis that just passes through the center, but perpendicular to the transverse axis, is called the conjugate axis. And then if you look at our formula, basically our standard form, it looks just like our ellipse. The only difference is we have a minus instead of a plus. So that minus makes a big difference, and it's also important is to note which one is the positive and which one is the negative value, as that will impact our graph as you'll see in a bit. All right. So our standard form of our hyperbola, again, like I just talked about, it's that same form, except instead of a plus, it's a minus. It is horizontal, like we just looked at, when it's the x squared minus the y squared. So when the x squared is positive, it is horizontal. But when the y squared is positive, it's then what we'll call a vertical hyperbola. So here, this is y squared minus the x squared. And notice we keep the b's with the y's and the a's with the x's. Some textbooks and websites will do that a little bit differently, but just like what we did with the ellipse, the b stays with the y's and the a's with the x's. All right, so on your screen, you can see 4 different hyperbolas graphed. If you can see them, you should be able to. I'm using the same a's and b's. They're just switching places. So I have 16 and 9 on all of them. They're just switching places on some of these. And then I always have the same center. So the center on all of these is 2, 1. So the differences that you see are the 16 and the 9s are switching places on half of them. And then on the other half, I have my x squareds being positive, which makes them be the horizontal hyperbola, and then the y squareds being positive, which makes them be the vertical hyperbola. So I just want to dive in a little bit about just the details about how we graph these hyperbolas. But before we do, I want you to take a look at the relationship of these four graphs. So just with those subtle changes, we get some pretty significant different looking graphs. There's this rectangle on all four of them. This rectangle would go exactly around the ellipse if that was a plus. More specifically, the vertices basically of the ellipse and then the other two dots on the rectangle would be the same vertices of an ellipse. If I just replace the hyperbola, replace the subtraction of the hyperbola with a plus, those would be the vertices of the ellipse. But with that one change of it being a minus, we all of a sudden get this vastly different graph. So let's go into this a little bit. So let's take a look at the steps of graphing a hyperbola. So first thing I would do would be to determine whether this is a horizontal or vertical ellipse. Since it's x squared minus the y squared, so since the x squared is positive, it would be a horizontal hyperbola, which will look like this, where it's on this, they shoot off in the right, and to the right and to the left. All right, and then you should take a look and see where the center is. So we have it's centered at 2, 1. And then just like if this was an ellipse, I would notice that with the 16, I would go from my center left and right 4, because it's square root of 16. And then with that b, which is 3, the square root of 9, I would go up and down 3. So like I said earlier, these 4 points would be the points of the ellipse. So I could swoop my ellipse, find my major and minor axes, and I would be done with the ellipse. But instead of this being a hyperbola, what we're going to do is we ultimately need to get these diagonal asymptotes. So with these asymptotes, if you notice, they go through the corners of this rectangle that I've drawn. So I need to get this rectangle. The rectangle's midpoints, the midpoints of the line segments that make up the rectangle, are those what would be the vertices of my ellipse. So you can use this to expand your rectangle into, and in this case it would be an 8 by 6 or a 2a by 2b size rectangle. We call this rectangle the fundamental rectangle. So just take your center, go left 4, right 4, up 3, down 3, and draw a rectangle that fits around that, and that's your fundamental rectangle. All right, then find your vertices. So since this is horizontal, my vertices that I'm interested in would be on the horizontal direction off of center. So not the up or down, but the horizontal. So they're my vertices. And you can do that also by then graphing your transverse axis as well. These foci are nice to graph, and we'll end up graphing them, but they don't really impact our the steps I need to take in order to graph this. They're just a nice detail that I'm going to require you to graph, but they're not fundamental for you finding out where the dots go. So once you have your vertices done and your rectangle, all we need to do is then draw straight lines that go through the corners of these rectangles. I like to do them dotted, typically usually yellow, because those are just our guides. They're not actually part of the graph. And then once you get that done, these are asymptotes. So I start at my vertex and I start going up and getting closer and closer to the asymptote, and then do the same thing on the other, passed over, and then do the same thing on the other side, and then do the other point for the vertex, going up, getting closer to the asymptote, and going on out in the other direction. It does touch those dots. So if I was to be doing the domain of this particular graph, it would be from negative infinity all the way up to this -2 square bracket, and then union, and then picking up at the 6, so square bracket 6, all the way to infinity. So there's nothing right here that's a part of the hyperbola. It's empty space, and I am touching that -2 and that +6. If I was to be just looking at one of these hyperbolas, they are notably not parabolas. These are not two parabolas just going in opposite directions. If I was to zoom out a bunch, this would just basically look like a V that's been rounded where it turns around instead of coming to a point. We like to think of the parabola as like a U. It is always getting steeper and steeper and steeper, like the parabola that goes up like that. It is always getting steeper and steeper and steeper as you go further to the left and to the right towards that positive negative infinity. But in this case, the hyperbolas are actually approaching linearity. Their slope is ever changing because it doesn't actually ever get to the asymptote, but it's basically getting closer and closer to being this line and not necessarily steeper and steeper and steeper like what we're seeing with the parabola. All right, so let's take a look. Now that we've seen how to graph one, and we can see these subtle differences between whether the y is positive or the x is positive, and then whether the rectangle is tall or wide. Let's take a look and let's do one from start to finish. All right, so when we're going to solve this, deal with this hyperbola, we're going to do all these things, a through j. But ultimately, in order for me to be able to graph this, if all I cared about graphing and no labeling or extra things that me, your teacher, would be concerned about, the things we would need to do is we would need to deal with completing the square if we need to. So if we're given to in this form, we must then complete the square. So then determine which direction it opens, what's the center, then figure out your A's and your B's to plot your fundamental rectangle. Then just graph the lines that go through the corners of the fundamental rectangle to get your asymptotes, and then at your vertices, then just swoop it and you're done. So it's not really tons of steps. A lot of this extra stuff is really extra mathy things that I'm going to be concerned about because that's my job to be concerned about those things. But really, like I said, complete the square, find the center, find your rectangle, graph the asymptotes super quick. They're just lines, and then swoop your hyperbola according to the direction it opens. That's it. So let's walk through this. So we have our equation of a hyperbola. I know it's a hyperbola because we have two different squares, and if I multiply a and c together, we end up getting a negative product. So because it's a negative product, it's less than 0, it's going to be that hyperbola. Basically, the a and the c have opposite signs. And this isn't quite in general form. General form would put that x over here, but it's already grouped together with our x's and y's. So let's complete this square. So I add this, the 57 to the other side. Then I factor out the 4, factor out the negative, half the 4 square it, half the negative 6 square it. And so when I'm adding in here a 4 into the parentheses, but really onto this side I'm adding a 16, so I need to add a 16 to the other side. And then here I'm adding a 9, but actually really into that whole set I'm adding a negative 9. So if I'm adding a negative 9 to this left side, I need to add a negative 9 to the right-hand side. Add those up, you get 64. Then divide everything by 64, stuff's going to reduce, and we end up with 16 in the denominator there, and then just 64 in the denominator for the right term. All right, so there it is in my standard form. Because the x is positive, it's going to be horizontal, so that can easily get my h and k. It's going to be -2 and +3 for my center. And so because it opens horizontally, my transverse axis is going to be horizontal. So that means that it's the y value of the center, so y equals 3. All right, so just to understand this graph in steps a little bit, I haven't done it all at once. So in order for me to graph my fundamental rectangle, I'm going to go to my center, which is left 2, up 3. And then I'm going to graph left and right 4, then up and down 8. So left and right 4, and we'll get these points. So these points that I've just highlighted, I'm not even really adding dots, I'm just highlighting them there for your benefit. That's my that's where the vertices of the ellipse would be. So we'll go left and right 4, and then up and down 8. So these highlighted dots are the midpoints of the rectangle. So basically from those points, you can just go up and down 8 again, and then left and right 4 again, and that is your rectangle. All right, so there we have our fundamental rectangle. But because our transverse axis is this y equals 3, and it's opening horizontal, then I know already that my vertex, actually rather my vertices, are going to be here. So -6, 3, and +2, 3. That's what I've done next are my vertices, right there. All right, then for teachery reasons, I'm interested in you finding and locating the foci. So my first focus is here, my second one's there. How did I do that? Well, I found my focal length. So let's take C, and it's the square root of a squared plus b squared. So that's 16 and 64, like we saw in the original problem. And then so it's square root of 80, which is 4 square root of 5, or it's just almost 9. This was 81, this would be 9, so we know that it's just a hair less than 9. So it's about 8.94 if you used a calculator. So I'm going to be at -2, -2, and then basically almost subtract the 9, and then -2, and then add the 9. Again, don't overthink trying to need formulas. If you look up on the internet, you'll see formulas that cover this, but really, guys, at the end of the day, that's not necessary. Just know that here's my center. I know my hyperbola is gonna be something like that. So that means my foci have to be there and there. So if you were to go to your 5th grade self and say, 5th grade self, I'm at this point and I need to go right 9 and left 9, help me find that point. But they're just gonna be like, dude, just count over 9 squares in each direction, and there you're gonna be. So, well, that's what I've done here. So I have here, I've gone right almost 9, left almost 9, but technically it's the plus or minus 4 times square root of 5, and that's where I graphed my foci. All right, and so notice I have my vertices graphed, my foci graphed, and then really, if I didn't care about the equation, just graph dotted lines that cross through the corners of the rectangle, and you're in business. But I am asking for the equation of those asymptotes. So let's talk about this. So I know that this is a rectangle, and if I'm passing through the corners of this rectangle, these lines are also going to be passing through the center of the rectangle. So that's just a property of quadrilaterals that you should know from geometry. So I have a line, and I know an x and y point, that is the center on both of these asymptotes. So I can just use y equals mx plus b, replace the y, replace the x with the x and y from the center. I know my slopes. My slopes are going to take on always b over a and negative b over a. So let me go back to my this picture here. Actually, let's go back to this picture here. So my slope of this yellow dotted line is always going to be a rise of b, a run of 4, regardless of what the b and what the a is. It's always going to be up b over a. And then for the other one in the other direction, it's always going to be down b over a. So it's always going to have a negative b over a slope. So basically, the slopes of these two lines is plus or minus b over a. So my slopes are plus or minus b over a. So that's plus or minus 8 over 4, or just plus or minus 2. So dealing with using the negative slope here, I can plug in my x for my center and my y for my center, and then solve for my y-intercept of b, and I end up with y equals negative 2x minus 1. So notice it's crossing through the y-axis at negative 1, and it has a slope of that negative 2. And then do the same thing over here, but this time it's a positive 2 for the slope, and I have a y-intercept of 7, and that's what I get when I just cross intuitively and just go through the corners. All right, just notice about labeling system. If it bothers you running all these words in the ordered pairs, as long as you have your numbers on your x and y axis, you can do something like this. You can label your labels basically. So right here in the math, I'm going to say that this is L1 and this is L sub 2. And so on my graph, I can just label this as L1 and this is L2. Or more formally, you might have heard me say L sub 2. This is L subscript 1, so we often will read that L sub 1 or L sub 2. All right, so all that's left to do on this graph is just to swoop it. So I have my vertex, so know it's going to touch this point and then start going up and then getting closer and closer to that line. Same thing here, starting this point, basically start going down, oops, too far, and getting closer and closer to the line. Over here, swooping up, going to the line, swooping down, going to the line, never touching or crossing, and always getting closer and closer to those asymptotes. All right, so here's what that looks like. So there's my This black dark line is the hyperbola. Together, collectively, it's a hyperbola. There is empty space here. There is nothing between these hyperbolas, and we do have they do touch at those vertices. So if I wanted to find the x and y intercepts, well, in this particular case, we don't have a y-intercept because it's not crossing the y-axis. If it was, I would let the x be 0, plug it in, and solve. For my x-intercepts, I'm going to do just that same thing, but for the y's. So I'm going to let y equal 0, so I'm going to plug in a 0. When I do this, I don't want to work with a fraction, so I'm going to multiply everything by 64. So I end up with 4 times x plus 2 squared. Negative 3 squared is just my positive 9, so it's minus 9. Then multiply everything times 64, so that's reduced to 1, and we have a 64 on the right-hand side. Solve them down, and you get negative 2 plus or minus the square root of 73 over 2. Notice this negative 2 is the x value of the center, and 72 is about square root of 73 over 2 is about 4.2. 73, square root of 73 is about 8.5. So half it, you can think of it about 4 1/4. Technically, it's a little bit more. So notice how that works out. I'm at negative 2 plus or minus about 4 1/4. So there I've just labeled my x-intercepts x1, x2 based upon how I've labeled them there. And then lastly, for my domain and range. Well, my domain, like I reminded you a second ago, there is nothing in between these graphs. From this vertex to that vertex is 2a units wide of nothing. So we say that our domain is from negative infinity to negative 6. Square bracket, we are touching here. This hyperbola touches at that dot. This rectangle is not an asymptote. We only have these 2 yellow asymptotes. That box is sort of kind of just a guide to create the asymptotes. All right, and then we pick up from 2 and head on to infinity. All right, and then our range, we're going to go down forever and ever and up forever and ever and everywhere in between. So it's negative infinity, positive infinity, or y is all real numbers. All right, so there you have it. This is the last of our conic sections. This is the hyperbola. Notice how it puts everything together. If you know how to do the ellipse, you can do this hyperbola. So take a look at these notes again if you need to. Let me know if you have any questions, and take care.